Lesson 2.6, Continuous Compounding. The introduction article, How Can Interest Be Compounded Continuously, has all of the information that you'll need for background to be able to do today's lesson. Some key terms you need to know are limits, continuous compounding, function, and rational function. Example number 1. Given a quadratic function f of x equals x squared plus 3x plus 5. As the values of x increase to infinity, what happens to the values of f of x? So we're going to investigate this using a table. So we need to make an xy table. It says as the values of x increase to infinity. So we're going to start with 1, and we're going to start jumping quite a bit. So 1 to 100, we'll then do 1,000, we'll then do 90,000. We're supposed to go to infinity, which means we're going to slowly analyze as our x values get bigger and bigger and bigger, what is actually happening. So I'm going to try these x values. Notice they're increasing and getting larger and larger and larger. We'll never actually get to infinity. It's just the x's are going to be increasing. You need to use a calculator. If you don't have a calculator, use Desmos. You're going to plug these values of x in to this formula, and you're going to solve for f of x, because f of x is the same thing as y. F of x and y are the same exact thing. So we're going to analyze what happens to the answers when you use these x values. So plugging in 1 to this function, I got the answer 9. 100 into this function, I got 10,305. Plugging 1,000 into this function, I got this number. Plugging the rest of the numbers into this function, these are the answers I get. So my x's got larger. As my x's increase to infinity, what happens to the answers, the values of f of x? I see they're getting bigger and bigger, and it doesn't look like it's going to be landing on any one number soon. They're not getting close to anything. They just keep getting larger and larger and larger. So it looks like the answers are also going to infinity. So I notice that there is no bound. It's not getting closer to one specific number in question. This means that your answers for f of x have no limit. So f of x has no limit. There's nothing that's like getting closer and closer and closer to where I can say, hey, look, it's going to stop here. It doesn't look like it's going to stop. It just keeps going. So it has no bound, which means it has no limit. So what happens to the values of x? It has no limit. It has no bounds. That is your answer. So let's go ahead and check your understanding. As the values of x increase toward infinity, what happens to the values of g of x? So we have another function that we have to use. We're going to do another table. Again, it says as the values of x increase towards infinity. So we're going to start small, and we're going to do rather large hops, and our x's are going to get slowly closer and closer to infinity. So x's slowly started getting closer to infinity. What is going to happen with our g of x's, our y's? So plugging in 1 to this entire function, I get negative 4. 100 into this entire function, I get negative 499. Plugging in 1,000 to this entire function, I get negative 4,999. 90,000 into this function, negative 449,999. Continuing. So I see that it does not look as though we are focusing in on one number. It just keeps getting smaller. And why do I say smaller? It's getting smaller because they're negatives. So the negatives keep getting bigger and bigger and bigger, which means the number itself is just getting smaller and smaller and smaller. It doesn't look like it's going to be stopping at any point. So they're decreasing because they're continuing to get larger in the negative direction. I notice that they're decreasing, but they're decreasing with no limit. It doesn't look like they're going to stop anytime soon. Example number 2. Given the function f of x equals the big fraction of 6x minus 1 all over 3x plus 2, as the values of x increase to infinity, what happens to the values of f of x? So again, new table. You'll notice I added another 1 in here. So we want to see what is really happening as we keep getting closer and closer and closer to infinity. As we just keep getting increasingly, absolutely huge. What's happening to our f of x? So we're going to use all of these values, type them into this function, and get the following answers. So as x's kept getting larger and larger and larger, our f of x's kept getting bigger, but you'll notice that they kept zooming in on the same one number. Every next step kept getting another 999, 999, 999. Like it kept getting closer and closer to, it looks like it's getting really close to the number 2. So as I'm looking at these, they're getting closer and closer and closer to the number 2. There's a mathematical way of writing this. So we are looking at the limit. As we are allowing these x's to get larger and larger and larger towards the infinity direction. Analyzing your f of x answers, we're noticing they're getting closer and closer to 2. So this is your math answer. How do you read this math answer? So you would say this as the limit of f of x as x approaches infinity is 2. Now what part of this function actually is this sentence? So I see it's a limit. So you're going to say the limit, what are you taking the limit of? You're taking the limit of this f of x. So the limit of f of x, got to say when you're doing it. So as x approaches infinity, because there's an equal sign, equal always means is. And what is it equaling? It's equaling 2. So the limit of f of x as x approaches infinity is 2. Let's go ahead and check your understanding. If f of x equals the fraction 1 over x, create a new table and use your calculator to find the limit of f of x as x approaches infinity. So here's my new table. It tells me my x's are going to get closer to infinity. So I'm looking to see what happens to f of x as my x's keep getting bigger. So I need to plug these x values into this formula. And when I do, this is what I get. So I notice they keep getting smaller, but it looks like it's getting increasingly smaller and smaller and really close to 0. It just might not actually ever reach there. So I realize it's getting closer and closer to 0. So it asked, what is the limit? So the limit of f of x, as we looked at x getting closer and closer to infinity, we observed it was getting to the 0. So the limit of these f's, when we used our x's going to infinity, we noticed he was getting closer and closer and closer to 0. This is you calculating your limit. Example number 3. Given the function f of x equals 2 to the x power, find the limit of f of x as x goes to infinity. So we have our table again. Plugging in 1 into this, I get 2. Plugging 100 into this, I get a very large number. And as I plugged more of these in, my calculator ran out, but they just kept getting obscenely large. They were just getting so large, they just never stopped. So it kept getting bigger and bigger and bigger, and it never ended up stopping. So that says that the limit of f of x as x was going to infinity, it's undefined. It was boundless. I couldn't find anything. I mean, this got big, and then it just blew off my page. I can't even write it. So it is undefined. Now let's check your understanding. Given the function f of x equals 1 to the x power, find the limit. I don't want to do a table. I want you to think about this. This says 1 raised to any exponent. The exponent represents how many times that 1 is going to be multiplied together. No matter how many times you multiply 1 together, you're still going to get 1. Like 1 times 1 is still 1. 1 times 1 times 1 times 1 times 1 times 1 times 1 is still 1. No matter how many times you multiply together, you're still going to get 1. So the limit of f of x as x approaches infinity, your answer is just going to be 1. It doesn't matter how many times you multiply together, you're still going to get 1. Example number 4. If f of x equals the quantity of 1 plus 1 over x, all to the x power, find the limit. We need a table for this one. Plugging all of these values into this big function. So yes, it's going to be in the equation twice. So what happens? It's a denominator and an exponent. 1, I get 2. Plugging in 100 into this function, and then continuing with all the other numbers. So I observe it's getting closer and closer. Like the whole numbers are always 2. Then you always have the decimal. Then it's followed by 7, and then by 1s, and then by 8s, and then by 2s, and then by 8s, and then by 1s, and then by 8s. I see it is getting closer and closer to this decimal. So I noticed it started repeating that decimal, and if we kept getting larger and larger, the decimal would continue to go on. This is actually a number, similar to how pi is a number, 3.14, and it continues to go on. I just don't know the rest of it. This is also a number. This is pi. We call this the number e. So he has a variable. He's getting closer and closer to e. So it asked, what is the limit? So the limit of f of x, as x is approaching infinity, it's getting closer and closer to our friend e. Let's go ahead and check your understanding. Set up a table and use a calculator to find the limit of 1 plus this fraction, all raised to the x power, as x goes to infinity. And then it says to round it. So it wants us to make a table. And it wants me to have my x's go to infinity. Plugging 1 into this big problem, I get 1.05. 100 into this big problem, get 1.05126. Plugging the rest of the values into this big problem on my calculator. I notice it stopped getting higher or lower. It stopped moving. So it looks as though this was its ending place. So the limit of this answer right here, as our x's kept getting larger and larger, of course, to infinity, we kept getting this. It said 5 decimal places. 1, 2, 3, 4, 5. Just happened to be my calculator stopped it there. So 1.05127 is my answer for my limit. Example 5. If you deposited $1,000 at 100% interest, compounded continuously, what would your ending balance be after 1 year? So we're going to use our compound continuously formula, where I need to know my B, P, R, and T. So reading the problem again. You deposited $1,000. That's my principal. And your interest rate is 100%. In a decimal, that is 1. Compounded continuously. That meant my n was going to be something about infinity because it goes forever. Never stops. What would your ending balance be after 1 year? Well, I can't use infinity as a number. So we're actually going to use that as the value x instead. So plugging this in. B equals, my P is 1,000. 1 plus my rate over x to the, my x is my n, my t is a 1. Simplify my exponents. You will recognize this. This is right here what we had on the previous page. We identified this as e. So that meant that this is b equals 1,000 times e. Well, I know what E is. E was a decimal. So we're multiplying the 1,000 by the decimal of E. And that meant B is $2,718.28. So depositing $1,000 out of 100% interest, compounding forever all the time for 1 year, you end up getting $2,718.28 after 1 year. So we have a continuous compound interest formula. B equals P times E to the RT. Continuous involves RE. So let's go ahead and look at example number 6. If you deposited $1,000 at a 2.3% interest rate, compounded continuously, so that means that I end up needing this formula instead, what would your ending balance be to the nearest cent after 5 years? So B, P, E, R, and T are the variables in the problem. E is not a variable though. E is actually a number that we're going to keep as E for right now because our calculator, just like pi, knows what the number E is. So if you deposit, rate is 2.3%, converting that to a decimal, compounded continuously, what would your ending balance be after 5 years? T is then 5 years. So B equals, here is my principal, E to the rate times your time. So I'm going to simplify my exponent. So simplify my exponents, that's 0.115. Typing all of this into your calculator, including the variable E, you end up getting B to equal 1121.87. So that meant that your ending balance after 5 years is $1,121.87. Now let's check your understanding. Craig deposits $5,000 at a 1.12% interest, compounded continuously. Compound continuously means that we are using this formula. What would his ending balance be to the nearest cent? So we have variables that we need to look at. Again, E is not really a variable. E is a number like pi, and our calculator knows what that number is, so we're going to leave it as E. Reading the problem again. Craig deposits $5,000. That's my principal. At 1.2% interest rate, which I need to change over into a decimal, compounded continuously for 4 years. So B equals, here is my principal. E is raised to the exponent of, here is my rate times my 4 time. I need to multiply the exponents together, so he is in simplest form. So this is E to the 0.0448 exponent. My calculator knows E, so typing all of this into your calculator exactly the way that it reads, this is the number I get. So what would his ending balance be? It is $5,229.09.